All right, so welcome to the eighth lecture. So far, what we have done is we studied testing of hypothesis. We found the point estimation, maximum likelihood estimator, and everything we did. But now we'll be sort of changing our approach for a couple of classes. We'll be starting the foundation behind all those, namely the central limit theorem. Okay. So in particular, this is from the chapter 5 of the textbook. So we'll be studying that. So let's get started. So this is lecture 8. Okay. So in this section, we'll be studying the limiting distributions. Okay. So it's called the consistency and limiting distributions. Okay, so there are a couple of important concepts. So let me first go over those concepts, and then we'll talk about how we can implement this and how we can see those hypothesis testing results in a more theoretical format. Okay, so for the first aspect which I want to discuss is the convergence in probability. Okay, let's see. Let's try to make it formal. So here's a definition for the convergence in probability. So let's consider that xn be a sequence of random variables and let x be a random variable defined on a sample space. So basically, we have this bunch of xn's and this x defined on the same sample space. Okay, so we say that xn, this sequence, converges to or converges in probability to the random variable x if, now we'll be using a little technical definition, which is very common for the convergence, if for all epsilon bigger than 0. So let's see. So let's consider this one. So xn minus x, this quantity bigger than 0. Now, the hope is if this xn and x are very close, their absolute value, the difference is no matter what I give you, the difference is actually xn minus x bigger than epsilon. It will be, if I compute the probability of this one, and if I take the limit, n goes to infinity, that would be 0. So the idea is xn and x are very close together. So that means that their difference is very small. Here we are asking for some, that they're different in certain probabilities, but what you're saying is that the limit of this thing as xn goes to infinity is always 0. Okay. Another version, or equivalently, if here I wrote it in terms of bigger than equal to epsilon, if I write it in terms of less than equal to epsilon, it'll be same as xn minus x less than epsilon is equal to 0. Okay, so we compute bunch of probabilities. So note that here we compute all these probabilities. Okay, and then as n goes to infinity, these probabilities are going to 0. Same is true for here. We compute bunch of probabilities as n is going to infinity. Sorry. So this is 1. The second one is 1 because xn is going to x. So as we are computing a bunch of probabilities, and as n goes to infinity, this is going to 1. Okay. If so, we write xn is going to p, xn going to x in probability p. Okay, so that's the notation. This p here is understood in terms of this one. It's called the convergence in probability. Okay. Now, suppose in many cases the limiting distributions for x. So this x may be a constant function. So what is a constant random variable? So constant random variable means if I have a random variable like x, and here is a probability. Suppose this random variable takes a particular value, say theta, and it's probability 1. So in this case, we say x is theta, a constant. So that is a constant. It's no longer a random variable, but if I insist on calling this a random variable, so x equals to theta. It is basically the entire mass is at one particular point. Okay. All right. So so the value of x is theta. Okay. Now it turns out that well, if so, here's an aside. Here's a note. If x is constant, so now we're talking about really a random variable. Since it's a constant, we'll call this we sometimes call it x degenerates to be a constant, or we call it a degenerate random variable. Okay, degenerate random variable. Okay. With all its mass at some constant value theta. Okay, so here as we wrote it like x theta with probability 1, and then we write xn is going to theta in probability. So if the limiting distribution is something like this one, which is just constant, by constant I mean x is the theta equals to 1 has all the mass, then we write this way. Okay, now this is just an aside. We will be dealing with many cases when it degenerates to be a constant. So I just wanted to let you know that this is a special case. Okay. Now, let's consider something which is a very famous property in the probability theory, which is called the weak laws of large number. Okay, but before doing the weak law of large number, I want to mention one theorem which you may have seen in the previous course or may not have seen in the last course, but I'll just write it. It's called the Chebyshev's inequality. Okay, what is that? It goes like this. So let x be a random variable with finite variance. Okay, this is important. We must have this as finite variance, sigma squared. So sigma squared is not infinite. Then for every k bigger than 0, there are various versions of it. I'm writing this version, x bigger than x minus mu. Sorry. Let e of x be equals to mu. By the way, if it has finite variance, mean should be finite. I mean, mean should also exist, right? Now, x minus mu bigger than k sigma is less than 1 over k squared. Okay. So this result is known to be as Chebyshev's inequality. I'll not prove it, but we'll be using this for proving the Wick law of large numbers. So let's write this now. Now, theorem, which is called the Wick law of large number. It goes like this. Let xn so suppose we have xn be a sequence of IID random variables having a common mean equals to mu. So it's IID. So each of this random variable will have the same mean. Let's call this mu, and variance sigma square. And I would like sigma square to be finite. Why? Because I'll be eventually using Chebyshev's inequality, which needs finite variance. Okay. So finite variance. Let xn bar be equal to it's a sample, so-called sample mean. Like if I choose the first n numbers, and if I compute the mean, that is my xn bar. Then the Wick law of large numbers say that then it's very simple. It says that x bar, it converges to mu in probability. So xn bar, it's converging to mu in probability. So that means, remember, so that typically if this n is fixed, so if this n is fixed, we denote it by I have a mix of notation, so let's write this on I. Yeah. So what I'm doing here is if I have, say, x1 plus x2 plus xn over n, right? So if I have this quantity, if I'm just adding up n terms, I'm calling this xn bar. Remember that previously, I mean, for a given sample, when n is fixed, we call this x bar. Okay? When n was fixed, we called it x bar. But here, we will let n change. So that means what is going on is that initially maybe we'll be starting with x1, then it'll be x1 plus x2 over 2. So our sample size will change. So our sample size will be changing, and it's growing eventually, right? So maybe when you have 10 objects or 10 samples, so we have x1 through x10 over 10. So that would be x10 bar. So so in other words, our sample size will change. Okay, and that's why we need a notation of the sample mean, which is dependent on n, and hence we write this as xn bar. Okay, what we are saying is that if these are drawn from a sample where the like it's a sequence of IID with mean mu and variance sigma squared, we are saying that this xn bar, so the sample mean as the sample is growing, is converging to the population mean. Now we are now understanding this convergence is in much more detailed way. So this is convergence is in probability. Okay, so that means it's exactly the way we defined earlier. So that means that xn bar minus mu less than epsilon, for every epsilon, the probability as and if we take n goes to infinity, that would be 1. So I'm talking about this one. All right. So let's prove it. It's a very quick proof. So let's prove it. So proof. So we'll be using basically the um, mean, and so we know that what is E of xn bar. So it's remember this xn bar is our old friend x bar. Okay? So I'm just specifying n. So it is mean we have. And what is the variance of xn bar? We have seen it before. It's sigma squared over n. Okay? So these are sample mean and variance. I'm sorry, it's sample mean and the expected value of sample mean. So this one is this one. And this is the expected value of sample variance. Expected, sorry. This is not really the expected value. This is a variance we're computing. So let's write it down. So this is the variance of sample mean. Okay. So we have expected value of sample mean, which is given by mu, and variance of sample mean, which is given by this one, right? So we know, I mean, we have seen before. So the only confusing part may be that so far we call this as x bar, but now it's n. But as I'm explaining, that we'll be eventually making this n larger. So we are trying to show the dependence on n. Okay. Okay. Now by Chebyshev's inequality, so let's see what we can do. If we want to compute probability of xn bar minus mu bigger than epsilon. Again, in view of the definition of the convergence in probability, what we're trying to do, we're trying to show that. So in this case, this x would be like mu, this xn would be like xn bar, it's bigger than, so I'm trying to show that when limit is n going to infinity, this is going to 0, right? So let's prove it. So now, if I compare this with the Chebyshev's inequality, look at that. So Chebyshev's inequality is right here. So it says that, so this is the expected value of xn bar, right? So if I compare these two, it looks like we are in a match. So xn bar minus mu is x minus mu. But here we have epsilon. So epsilon got to be something like, I have to write this, I have to see this epsilon as some k times sigma, right? So let's write this. I know what it is. So it's probability of xn bar minus mu is bigger than k times sigma. So let's see, what is sigma? Sigma is sigma squared over n, right? So that is the variance for this. So let's take the standard deviation. So that's sigma. And therefore, it's really sigma over square root of n. And I have to compensate that. And I have an epsilon. So I have epsilon. And then let's write square root of n over sigma, right? So what I'm doing here is the following. So this is E of x bar, and this one is the square root of variance of xn bar. And that is exactly what we need for Chebyshev's inequality. We need here the mean, and we need the square root of the variance, which is sigma, right? Okay, so now this by the Chebyshev's inequality, this is less than, I'm using this one. So if I can figure out what the k is, it's basically 1 over k squared, right? So this is like my k. So I can write this as less than 1 over k squared. So 1 over epsilon square root of n sigma squared, okay, which is sigma squared n epsilon squared. So what we get is probability of, so let me just rewrite, probability of xn bar minus mu bigger than epsilon is equal to sigma squared n epsilon squared. So if I take the limit, so limit n goes to infinity, which is 0, right? For which epsilon is this true? For every epsilon. So for every epsilon bigger than 0, this is true. And hence, this is exactly the definition of the convergence in probability. So that means, hence, xn bar is converging to mu in probability. Done. It's proved. So that means when we are, so this is sort of the justification of something that we did earlier, that whenever we are computing, we are having something like a large sample and we are trying to compute a sample mean, that sample mean is tending toward population mean. Okay. Now there are some strong law of large number, which we'll skip here because I mean that needs something which is a little bit different, and we'll probably not use it that much. So this version is called a strong law of large number. Sorry, this version that we proved is called a weak law of large number. And there is a version called strong law of large number, and that is a little bit different. I mean, the assumptions are a little bit different. Okay. Now, we can have some fun results based on this one. So we'll prove this one, but I'll not prove the rest. So here I'll write this as a theorem. First one, suppose xn is going to x in probability and yn is going to y in probability. Then as you expect, xn plus yn is actually going to x plus y in probability. It can be shown. Okay. Remember, now going to this y in probability. So this is this has a meaning which we already explained. Let's write this as number 1. Let's write here. I'm trying to combine several theorems, and a, let's write here, and a is a constant. So I have a constant called a. Okay. Then number 1, xn plus yn is going to x plus y. Number 2, a times xn is going to a times x in probability. Number 3, suppose xn is going to a in probability. So suppose now Well, let me write it as a separate theorem because otherwise it will be confusing. Okay, so this theorem is very clear. Basically, if I just add two the sequences, and it's going to wherever each one is going, and this going to is in sense of the going to in probability. So it's a convergence in probability. A times xn is going to a times x in probability. So that's the second result. Let's write the other one, which is also very important. So here is another theorem. So it goes like this. So suppose xn is going to a in probability, and the real function g is continuous at a. Okay, what does it mean? So remember that this is the, so xn is converging to something which is just a. So what is that? What is the meaning of that one? So a, which is probability 1. So this is where it's converging to. So here, suppose this random variable is x. xn is converging to x, where say x is this one. I drew x here. So corresponding to a, its probability is 1. Okay, so it's a constant function. Okay. Now, what we are saying here is the following. So suppose we have a continuous function g. So that means there is a different function, say the g behaves whatever it does, but it's continuous, so it's gx. It's at least continuous at the point A. Okay. Then it may have discontinuity somewhere else, but it is continuous at A. Then g of xn is converging to in probability of g of x, or g of A in our case. Okay. So if if xn is converging in probability to A, then g of xn is converging in probability to A as g of A as well. Okay. All right. So it has many important corollaries, which I'll write. So let me just write a couple of those. So example, for example, I can take this g of x to be x squared. Okay. So if xn is converging in probability to A, and if I take g of xn to be x squared, xn squared, then xn squared is converging in probability to A squared. Okay. 1 over x, suppose my g of xn is 1 over xn, and for that I'll be, let's write this way. So then 1 over xn is converging to, in probability, to 1 over a, provided a is not equal to 0. What happens for a equals to 0? This gx is not continuous at that point, so the assumption does not hold. Suppose g of xn, square root of xn, then I can write square root of g of xn, square root of xn is converging to square root of a, for which a bigger than 0. Otherwise, there is a discontinuity. Okay. So these are the 3 examples where you can see that this theorem, the previous theorem where which is about G, is directly implemented. Okay. Let's write one more thing, one more theorem here. Theorem all this may look very trivial, but all these are to be proved. And if you look at the, I mean, for any text, they usually prove this. But here we're skipping the proof because um, some of the proofs will be not that difficult. And if you have any question, you can always ask me. So suppose xn is going to x and yn is going to y in probability. Then xn times yn is going to x times y. Okay. So addition, subtraction, multiplication, everything we have done. All right. Here the proof is very simple. So let me just quickly do this proof. So this one is basically, you can write xn times yn equals to, follow this carefully. So it's 1/2 xn squared plus 1/2 yn squared minus 1/2 xn minus yn squared. You can check, it's a simple algebraic computation that xn times yn can be written as this one. Okay. Now, once you're going to basically where it's converging to, so it's converging to, we know that xn squared is converging to x squared, yn squared is converging to y squared, and xn minus yn squared is converging to x minus y squared. Okay, and which is equal to, again, xy. So xn yn is converging in probability to xy. Done. So it's basically a combination of all the results that we have done. So we are basically writing xn minus yn in a certain way. And by the way, I forgot to mention one more thing. Let me just, it's a good place to mention. So this is true for if xn is going to x, yn is going to y, then not only xn plus yn, but xn minus yn is also going to x minus y. Okay? It's true for a plus or minus, it doesn't matter. So what is happening here is basically xn minus yn is going to x minus y, and then you consider the function g. So this is true. You can check. Okay, so this is about the theory. Now let's see if we can understand this in terms of what we are doing before, meaning how to understand this in the context of sampling and statistic. Sampling and statistic. Okay. Now, two important things will need. One is an unbiasedness of an estimator, and the second one is the consistency. So we have defined one, we never discussed the other one. So let me just recap. So we say that a point estimator T of theta is unbiased if E of t equals to theta. Okay, so this is the definition of the unbiasedness. Okay, so if you're trying to find the value of theta, and if you can find a statistic, so that if you can find an estimator t, so that E of t equals to theta, we call it unbiased. So this is unbiased. That's the first important concept. The second one is, and by the way, so recall that sample mean, and now I'm again using the notation x bar because my n is fixed. So for n fixed, which is a sample size, sample mean x bar, and the sample variance, which we wrote as s squared. So those are unbiased estimators of the sample, the population mean and population variance. Okay, are unbiased estimators for mu and sigma squared respectively. That is, E of x bar is mu and E of s squared is sigma squared. And note that the variance of the sample mean is not an unbiased estimator for the population mean. Okay. And we have discussed this for a long time, so we'll not repeat it. So this is the first one. So this is the unbiased definition. Now the second definition is about the consistency. Let x be a random variable, with the cumulative distribution function CDF f of x. But remember that the cumulative distribution function, as we have seen for the previous chapter, that usually it depends on many unknown parameters. Let's call that call those unknown parameters with theta. So meaning that it can be a scalar, it can be a vector. So where this theta belongs to some set omega. Let x1, x2 up to xn be a sample from the distribution So they are the sample from the distribution x, and let t sub n denote a statistic. Okay. We say that this Tn is consistent. So Tn is consistent estimator of theta. Remember, Tn is unbiased provided E of Tn is theta, and it's consistent provided this Tn is converging in probability to theta. Okay. So we have basically the definition of what we can call a consistent estimator of theta. And here we are using the concept of that convergence in probability that we developed. Okay. Let's do an example to see this object. So let's consider, say, example. Suppose x1, x2, all the way up to xn, they denote, so let that this is a sample from a distribution with mean mu and variance sigma squared. Okay. We have already seen that this the sample variance is an unbiased estimator of sigma squared. Okay. So we know that E of, let me just for the sake of because I'll have a convergence in probability, so basically my n will be floating. So let's now denote the sample mean by let us consider xn bar by 1 over n, I from 1 to n. Okay. We know that this xn bar is equal to mu. And we also know that the sample variance, which is s squared, which we'll write as s squared n, which is given by n minus 1 I from 1 to n xi minus x bar n. So I'm just specifying all the n's because we'll be varying the n. So we know that this, and then E of Sn squared is unbiased estimator of population mean. So that is something we already know. So here the only difference is we are using a different notation. Okay. Now, observe that by the weak law of large number. And let me show again what we did. So here is the weak law of large number right here. It says that if you have a sequence with this xn bar, then xn bar is converging in probability to mu. We have seen it. Okay. So then by weak law of large number, xn bar is converging in probability to mean. Okay. So that is something we already know. So there is nothing new for this one. Okay. Now we'll show, what we'll try to show is the sample variance converges in probability to sigma squared. So we'll be trying to show that Sn squared is also converging to sigma squared in probability. So let's write this down. So let Sn squared, so this is 1 over n minus 1, I from 1 to n, xi minus xn bar squared. Okay, so now this one. Let's see if we can understand this a little better. So this is really, it's 1 over n minus 1. And if I simplify this, it's basically the same thing as we have done for the, like this. Okay, let me just do it anyway. So it's basically summation I from 1 to n xi squared plus xn bar squared minus 2 xi xn bar, right? So if I compute this, it's going to be 1 over n minus 1. And this first term would be I from 1 to n xi squared. Second term, it's a constant. There are n of those, so it's n times xn squared. Third term is this, it is a constant, so it will pull it out. So it's 2 xn bar, and then we have a summation of xi, right? So which is summation of xi means it's basically xn bar times n. So it's n times xn bar. That's it. So I simplify it. And again, I mean, if you are familiar with this kind of computation, it should be very easy for you. So it's I from 1 to n xi squared, and then there is n, there is 2n, so it's minus n xn bar squared. Okay. Now, this part should remind you of the variance, provided I can write this in the following way. So suppose I write this in the following way. So I write this as n over n minus 1. So basically, what I need is I need here n over n minus 1 and here 1 over n minus 1, right? So I have to cancel this n for the first term. So I write I from 1 to n xi squared, and here it's fine, xn bar squared. So that's what we have. Okay, so this is my Sn squared. So now let's see if we can see where this Sn squared is going to. Okay, I'll try to understand this separately. Okay, so the goal is want to see where Sn squared is going in probability 2. So what is this question mark? Okay, now let's see if we can figure it out. So here we observe that let's consider the first quantity. So 1 over n summation I from 1 to n xi squared, right? Where this, let's call this one xi squared to be yi for a moment. So this is going to be 1 over n summation yi I from 1 to n. Let yi be xi squared. Okay. So what you get here is really in our term, it's yn bar, right? Therefore, E of yn bar, what is that? What is the expected value of this quantity? So it's basically 1 over n summation I from 1 to n E of yi, right? Which is 1 over n I from 1 to n E of xi squared. Now, xi's are from IIT. Okay? So xi's are sample, hence they are IID. They are independent and identical distributed. So that means E of xi squared is actually equal to E of x1 squared for every I. And it's not really true for, I mean, it's nothing special about this one. I can write any number here, right? So it's basically I from 1 to n E of, say, x1 squared, I write. There are n of those. I'm dividing by n, so it's really E of x1 squared, right? So that's my first observation. So what we are finding is following. So this quantity, so once again, going back, I'm trying to handle this quantity, right? So this quantity we observe, this is, we can write this as some yn bar, and this yn bar has the expectation of this one, right? Therefore, yn bar by is going to, by the weak law of large number. What do you know? So it will be going to E of x1 squared, right? In other words, this quantity, which is 1 over n I from 1 to n xi squared, which is yn bar. So that in as a whole, so this is going to E of x1 squared in probability by weak law of large number. Okay. Now we are in pretty good shape in the sense that let's talk about this one. So here, what do you have? So let's take n goes to infinity. So let's call this by equation number, say star. In star, take n goes to infinity. So what we have is Therefore, in probability, then we have seen before that as this one is going to E of x1 squared, where does this one go to? So we have xn bar squared. So xn bar is going to mu. So xn bar squared would go to mu squared, right? So this part also xn bar squared is going to mu squared. Here we don't really need, let me just, there's two. Let's write this way. Also, xn bar squared is going in probability to mu squared. How do we get it? We can use any of these results that we proved earlier. For example, if xn is going to x, g of xn is going to g of x. Now xn is going to mu, right? Which is a constant function. So and suppose my g of x is x squared, so then xn bar squared is going to mu squared, right? Hence, from here, so basically, so Sn squared in probability going to, let's see. So basically, I have to take the limits for n here. So limit n goes to infinity, n over n minus 1. Then for this one, 1 over n, so this quantity is, we know where it's going. It's going to, where? It's going to E of x1 squared. We have already checked. And minus this, the second term is going to mu squared, right? And this limit is 1. So Sn squared is going in probability to E of x1 squared minus mu squared. Now let's see what this quantity is. So variance of x1 is sigma squared. They are IID with the mean mu and variance sigma squared, right? That we already know. Therefore, E of, by definition, the variance, A of x1 squared minus mu squared is sigma squared. So E of x1 squared is sigma squared plus mu squared, right? Or in other words, E of x1 squared minus mu squared is sigma squared. So that means Sn squared is converging in probability to sigma squared. I don't even need last one. Okay, so I need this one to be sigma squared. Done. So this is a very, very important result. With which really shows that the sample variance is also, I mean, not only the sample mean is converging in probability to mu, sample variance is also converging in probability to sigma squared. Okay, so both sample mean and sample variance are converging to where they should be. Okay. All right. Let's see. And therefore, remember that what we discussed about the consistency. So let's so we just defined the consistency, which says that if the Tn, a statistic, is going to wherever it should go in probability, then we call it a consistent. All right, so we just proved that. We just proved that Sn squared is going to sigma squared in probability. And we also know, we knew before that xn bar is converging in probability to me. Hence, we can say that this Sn squared is a consistent estimator of a sigma squared, and xn bar is a consistent consistent estimator of mu. Okay, hence Sn squared is a consistent with the definition that we already mentioned, estimator of sigma squared. Also, xn bar is a consistent estimator of mu. Okay, so that means both of these are unbiased and consistent estimators. So that's a very good thing. Okay. So here's the conclusion. So this Sn squared and xn bar are unbiased and consistent estimators. Okay, of sigma squared and mu respectively. Okay. All right. Let's now solve some of the problems to see how it works. So let's start by considering, say, the example, say 5.1.2. Okay. It goes like this, that suppose yn is a random variable from a binomial distribution with parameters n and p. Okay. First part, prove that yn over n, it converges in probability to p. So there are two p's here. Okay, so this p means convergence in probability. This p means the same p as before. Okay. So here's a proof. Very simply, let's consider, say, so yn follows a binomial distribution. So suppose we have, say, x1, so let x1, x2, etc. up to xn, they follows IID Bernoulli distribution with parameter p. Okay. So then E of xi for each of these would be p, and the variance would be p times 1 minus p. So this is my mu, and sigma squared is p times 1 minus p for this. Okay. So sigma squared is actually variance of xi, and this is true for I equals to 1, 2, up to n. Okay. Now, basically, this yn can be written as a sum of the Bernoulli distributions, right? So, because binomial is always the sum of the Bernoulli distributions. So hence, then yn, which is the sum of I from 1 to n xi. So yn over n is 1 over n I from 1 to n xi, and this is our old friend. We have been discussing with this one. So this is nothing but xn bar, right? And we know that this xn bar, where does it converge to? So xn bar is from here. It's x1, x2, xn. So from here we know. So hence, xn bar is converging in probability to p by Wick law of large number. Why? Because E of xn is actually converging to the expected value of each of those, which is P. So it's basically converging in probability to the expected value of the individual components, which is P. So xn bar is converging in P to in probability to P. And here I can write to P. So hence proved. Hence, yn over n is converging in probability to P. Done. First part. Okay. Second one is prove that 1 minus yn over n converges in probability to 1 minus p. Okay. Should be very, very similar to the last one. Proof. Take, for instance, g of x equals to 1 of x, which is continuous at all points. So then 1 minus yn over n, which is really g of yn minus over n, which converges in probability. We have already seen yn over n is converging to p in probability, so it converges in g of p, which is 1 minus p. Right? Done. So 1 minus yn over n is converging in probability to 1 minus p. Final one, C, prove that yn over n, 1 minus yn over n converges in probability to p times 1 minus p. Once again, it's very similar to the last one. So here's a proof. Suppose we consider gx equals to x1 minus x. Once again, it's continuous for every point. So then yn over n, 1 minus yn over n. So it's really g of yn over n, which converges in probability to g of, since this converges in probability p, g of p, which is p 1 minus p. Done. So this is the way to implement all the results that we have learned so far for various analysis. Okay, next problem. So let's consider same example. And we'll come back to this example later in the later section. So this is sort of important. 5.1.7. Okay. And follow this a little carefully. It goes like this. Let x1, x2, xn be IID, random variables, with a common PDF fx equals e to the minus x minus theta, or x is bigger than theta, and 0 otherwise. Okay. This PDF is called the shifted exponential. Okay. Now let's consider, so let yn be equal to minimum of x1, x2, xn. So we have a bunch of random variables, right? So we have x1, x2, xn random variables. So suppose this yn is a minimum. Okay. prove that. Prove that yn is going to theta in probability by first obtaining the CDF of yn. Okay, so let's solve this one. So here's the solution. So first, we are trying to compute the CDF of yn. Now, what is yn? Yn is the minimum of all the x's. Therefore, if I want to, one easy way to compute it is, so suppose I start by computing the other side of the CDF, meaning that suppose we compute P of yn is bigger than a number. So y is a fixed number. Okay. So that means what we are trying to compute is P of minimum of x1, x2, xn. It's bigger than y, right? Now, if the minimum of all this is bigger than y, that means each and every one should be bigger than y, right? So that means probability of xi is bigger than y for every I. Okay. Now, since these xi's are IID, that means I can write this by taking the, so there are n of this inequality. So I can write this by taking the product of all the corresponding probabilities. And what are those? So I can write this as probability of, say, a general random variable. So we have x1, x2, xn. So they are from the same distribution x. Now, if we are saying that they are ID and their distribution, the common distribution is x, I can simply write probability of x bigger than y, right? And how many are there? There are n of those. So I write to the power of y. Okay. Now, how do we compute this quantity? So this quantity can be computed using the PDF. The PDF is right here. Okay. Now, this PDF is telling me that if so, how do you compute this? This probability density function 0, provided x is less than theta. Okay. So if your y is, say, there are two cases. So suppose, follow this carefully. So if y is less than theta, so we have a PDF function. So let me just draw the PDF here. So here is a theta. The function is exponential. It's 1. Okay. So before that, it's 0. So this is the PDF. So fx. Now, suppose we have our y, which is less than theta. So if y is less than theta, then what is the probability of x more than theta? Well, if I have this y somewhere here, then basically I'm computing for this probability the entire area of the curve, which is 1. So this is 1 if y is less than theta. And if y is bigger than theta, that is the interesting case. So if y is here, so then I'll compute this corresponding curve. So it's basically, I'll be computing, say, y to infinity, and then the probability density function, which is e to the minus t minus theta dt to the power of n. And you can check that this computation would give you that this is e to the minus n y minus theta. I'll skip this computation. Okay. All right, so we have two distinct things. So we have probability of y bigger than little y. So little y is a number. Okay, so this is a number. So this y, this little y can be anywhere. It can be here, it can be here, anywhere. So this probability of yn bigger than y, we computed this way, and we found that depending on where that y is, if it's less than theta or more than theta, there are two possibilities. It can either be 1 or it can be something like this one. Okay. Now next. So therefore, so we are not done with the CDF yet, because CDF means so the CDF of this function, which is yn, is given by f of yn of say y, which is 1 minus probability of yn bigger than y. So it's basically 1 minus what we just obtained. So that means it will be what's the other version? So the previous one was 0, so it's now previous one was 1, so it's 1 minus 1, so it's a 0 if y is less than theta, and it's 1 minus e to the minus n y minus theta if y is bigger than theta. So there are two cases, right? We found the CDF, but I mean, we are trying to show something converging in probability. Okay, to show the convergence in probability, we have to go back to the definition. What I mean by that is the following. So we can write probability of absolute value of y. So if you recall the way we defined the convergence in probability at the very beginning. So this is the way. Let me try to find where we defined the convergence in probability. The very first page. So when we have this, if it's bigger than 0, and we compute this limit, it's 0. Bigger than epsilon, compute this limit, it's 0. Less than epsilon, compute this limit, it's 1. So let's pick up 1. So let's compute say this one. So yn minus theta less than epsilon. You don't have to stick to this one. You can just compute any one, like the other version is fine too. Now this is, what does it mean? So again, so yn minus theta is less than epsilon. It really means minus epsilon less than yn minus theta less than epsilon, right? So then what is the range for yn? So it's a theta minus epsilon, yn less than theta plus epsilon. So that is the meaning for this one. So let's put it here. So it's probability of theta minus epsilon less than yn less than theta plus epsilon. I can write this in terms of two CDFs. So I can write this as f of, so first I have to write the bigger area. So it's f of yn with this theta plus epsilon minus f of yn of theta minus epsilon. Now note this carefully. If it's more than theta, then its CDF is right here. If it's less than theta right here, epsilon is a positive number, okay? Epsilon bigger than 0. So the theta minus epsilon is less than theta, so it's 0. So I have this as 1 minus e to the minus n. So it's theta plus epsilon minus theta. That's this quantity. And this is minus 0. So what we get is 1 minus e to the minus n epsilon. We surely goes to, as n goes to infinity, this goes to 1. Okay. Hence, we finally checked what we wanted to check. So we finally checked that limit n goes to infinity, probability of yn minus theta less than epsilon is 1. What does it mean for us? So it means that, yn is converging in theta in probability. Done. Okay. All right, so this is one of those classic examples when we compute this quantity, which is very useful. Let's pause here because that is pretty much all we want to talk about, the first half of the story. Next time we'll be mentioning, so basically what we mentioned here, so these are some of the very important results, which basically based on the Wick law of large number. But next time we'll be stating some results which are very useful. And after that, we'll be continuing with the central limit theorem. So hopefully by next class, we'll be done with the central limit theorem and the understanding of that. And after that, we'll move again with where we left, meaning that we'll be starting with the follow-up of chapter 4. So hypothesis testing and everything, we'll study this in more details after we completed our discussion on the central limit theorem. Okay, thank you.